everyone, let's start the video with understanding the second law of thermodynamics. Energy is conserved in nature as described by the first law of thermodynamics. But how does energy flow and why do some processes naturally happen while others don't? Let's explore the second law of thermodynamics. For example, when you leave a cup of hot coffee in a cooler room, it cools down. Heat flows naturally from hot to cool, increasing disorder in the system. But imagine if the coffee got hotter instead. Sounds impossible, right? That's because it would violate the second law of thermodynamics. Similarly, transferring heat into a wire cannot generate electricity because heat is a disorganized form of energy. This illustrates why energy transforming is not always straightforward. This brings us to entropy, a measure of disorder in a system. The second law states that in isolated systems, entropy always increases, driving processes towards more disorganized states. What about thermal energy reservoirs? It is a system or body that can absorb or release a large amount of heat without undergoing a significant change in temperature. Take a look at this natural example in real life. Lake, large bodies of water act as thermal energy sink that absorbs the heat, while the sun and atmospheres act as thermal energy source that supplies heat to a system. Thus, thermal energy reservoirs are essential in analyzing processes governed by the second law of thermodynamics.
Carnot cycle is the first proposed in 1824 by French engineer Sadi Carnot. The Carnot cycle is composed of 4 reversible processes, 2 isothermal and 2 adiabatic, and it can be executed either in a closed or a steady flow system. Reversible isothermal expansion, or state 1, the temperature of the gas is TH, while the amount of total heat transferred to the gas is QH, and the cylinder head is in close contact with the source at temperature TH. The gas is allowed to expand slowly, doing work on the surroundings. As the gas expands, the temperature of the gas tends to decrease. But as soon as the temperature drops by infinitesimal amount, some heat is transferred from the reservoir into the gas, raising the gas temperature to TH. Thus, the gas temperature is kept constant at TH. Since the temperature difference between the gas and the reservoir never exceeds, this is what we call reversible heat transfer process. It continues until the piston reaches position 2. Reversible adiabatic expansion, or state 2. The reservoir that was in contact with the cylinder head is removed and replaced by insulation so that the system becomes adiabatic. The gas continues to expand slowly, doing work on the surroundings until its temperature drops from TH to TL. The piston is assumed to be frictionless and the process to be quasi-equilibrium, so the process is reversible as well. Reversible isothermal compression, or state 3. The insulation at the cylinder head is removed and the cylinder is brought into contact with a sink at temperature TL. Now, the piston is pushed inward by an external force doing work on the gas. As the gas is compressed, its temperature tends to rise. But as soon as it rises, heat is transferred from the gas to the sink, causing the gas temperature to drop to TL. Thus, the gas temperature remains constant at TL. Since the temperature difference between the gas and the sink never exceeds, this is a reversible heat transfer process. It continues until the piston reaches state 4. Compression, or state 4. When the low temperature reservoir is removed, the insulation is put back on the cylinder head and the gas is compressed in a reversible manner. The gas returns to its initial state, which is state 1. The temperature rises from TL to TH during this reversible adiabatic compression process, which completes the cycle.
Kelvin, Planck, and Clausius' statement states that the second law of thermodynamics limits the operation of cyclic devices like heat engines and refrigerators. The Carnot principle have 2 principles. For the first one is the efficiency of the irreversible heat engine is always less than the efficiency of the reversible one operating between the same 2 reservoirs. Second one, the efficiencies of all reversible heat engines operating between the same 2 reservoirs are all the same. To prove the first statement, consider 2 engines are operating between the same reservoir as shown in the figure 6.40. One engine is reversible and the other one is irreversible. Now, each engine is supplied with the same amount of the heat. The amount of work produced by the reversible heat engine is Wref and the amount produced by the irreversible one is Weref. In violation of the first Carnot principle, we assume that the irreversible heat engine is more efficiency than the reversible one, thus deliver more work than the reversible one. Now, let the reversible heat engine be reserved and operate as the refrigerator. This refrigerator will give the work input of Wref and give the heat and reject heat to the high temperature reservoir. Since the refrigerator is rejecting heat in the amount of QH to the high temperature reservoir, and the irreversible heat engine is receiving the same amount of the heat from this reservoir, the net heat exchange for this reservoir is zero. Thus, it could be eliminated by having the refrigerator discharge directly into the reversible heat engine. Now, considering the refrigerator and the irreversible heat together, we have an engine that produces a net work in the amount of Wref minus Wref while exchanging heat with a single reservoir, a violation of the Kelvin-Planck statement of the second law. Therefore, our initial assumption is incorrect when they conclude that no heat engine can be more efficient than a reversible heat engine operating between the same reservoir. The second Carnot principle can also be proved in a similar manner. This time, let us replace the irreversible heat engine by another reversible engine that is more efficient and thus deliver more work than the first reversible engine. By following through the same reasoning, we end up having an engine that produces a net amount of work while exchanging heat with a single reservoir, which is a violation of the second law. Therefore, we conclude that no reversible heat engine can be more efficient than the reversible one operating between the same two reservoirs, regardless of the cycle is completed or the kind of the working fluid used.
A Carnot engine receives 650 kilojoules of heat from a source of unknown temperature and rejects 250 kilojoules of it to a sink at 24 degrees Celsius. Determine the temperature of the source and the thermal efficiency of the heat engine. Let's start by writing down the clue from the questions. The engine receives 650 kilojoules of energy, so the QH equal to 650 kilojoules. Then it rejects 250 kilojoules, so QL equal to 250 kilojoules. The sink where heat is rejected to is at temperature of 24 degrees Celsius, so the TL equal to 24 degrees Celsius and plus 273.15 to make it in Kelvin, which equal to 297.15 Kelvin. We can start by using these equations QH over QL equal TH over TL to find the temperature of energy source since this is a Carnot engine. Substitute the values, then we get the TH equal to 772.6 Kelvins. Secondly, we use Carnot efficiency equations, which is efficiency equal to 1 minus TL over TH. Substitute the values and we get the answer is 61.5%. A heat engine operates between a source at 477 degrees Celsius and a sink at 25 degrees Celsius. If heat is supplied to the heat engine at a steady rate of 65,000 kilojoules per minute, determine the maximum power output of this heat engine. Let's start by writing down what we know from the questions. The source temperature, which is TH, is equal 477 degrees Celsius, and the sink temperature, which is TL, is equal 25 degrees Celsius. Then the heat is supplied at a rate of 65,000 kilojoules per minute. To determine the maximum power output of this heat engine, we need to find the efficiency first. So, use efficiency equal to 1 minus TL over TH, then substitute the values to get the final answer, which is 0.602. Next, we use efficiency equal to W net out over Q in, then rearrange the equations and write it in time rate form. Substitute the values and we get the maximum power output is equal to 652.2 kilowatt.